So, where are we at? We've spent most of this week doing number theory stuff, and today is more number theory stuff. So today's subject is solving congruences. So let's get right into it. We will start with a fairly simple case of linear congruences. So what are these? A linear congruence is an equation or congruence of the form AX is congruent to B mod M. So I'm putting equation in quotes because we're going to essentially think of it the same way we think about equations, solving equations. But technically speaking, equations are when you are saying some things are equal. And in this case, we're just saying that they are congruent. So it's maybe more appropriate to call it a congruence. Although if you're thinking about it happening in D mod M, then maybe you could say it's an equation, because here we're dealing with a fixed set. But I'm going to erase that. So, okay, a linear congruence is something that looks like this. And we can essentially think of it like a linear equation. AX equals B. Just because this, I think, should be a little bit more familiar, but you can see that it has essentially the same form. Some constant times some variable is congruent to some other constant, and we want to, as always, find the value of this variable, or find a solution. So one difference from these two cases is that a linear equation will have, one solution, or possibly zero. But a congruence can have many solutions. So let's take a look at an example. So let's say 2x is congruent to 5 mod 7. How are we going to solve this? So one way is that we can just start checking things, essentially kind of a brute force kind of way. So we're saying 2x is congruent, 2x is equal to 5 plus 7t for some t. So let's call this by inspection. 2x is equal to 5 plus 7t for some t. So essentially we're just asking, when is this going to be an even number, right? 2 times something. And so you can see that taking t equal to 1 will work. Then we want to ask, when does 2x equal, what is 5 plus 7? I think it's 12. So we find a solution, x equals 6. And so that's a solution to our original equation. But let's just check that. 2 times 6 is 12, and that is congruent to 5 mod 7. So that's what we wanted. But we also have so since we're working mod 7, we should be able to add 7 to our answer and still get a solution. So x equals 6, but x could also equal, what's 6 plus 7? I think it's 13, or 20, or so on. And let's just check this. 2 times 20 is equals 40. And this is also congruent to 5 mod 7, because 35 is multiple of 7. Cool. So this is just an example of what is a linear congruence and what does it mean to be a solution, and the fact that you can have many solutions. But this is kind of not a very satisfying way of solving it, because what was the content of that? I kind of just said, you just can see that this is a solution. It's not a really good way of generating solutions. So here is a better method. Or let me even just say, here is any method at all for finding solutions. So if we had a linear equation, let's go a little bit deeper into this analogy. How would we solve this? We would multiply by 1 over a on both sides, and we would find our solution is x equals b over a. And this is basically a surefire way of finding solutions to linear equations. And in fact, we can do a similar thing for linear congruences. So let's introduce a definition, because we don't know how to do this yet. So let's introduce that. An inverse of a mod m is an integer b such that a times b is congruent to 1 mod m. So this is, as you can see, very similar to what we mean by an inverse in general, right? The point of this being the inverse of a is that if you multiply them, you get 1. So we're saying the same thing in our modular arithmetic scenario. An inverse is something that when you multiply them, you get 1. And let's say if such a thing exists, it's unique mod m. So I will leave that as an exercise, I think, to prove that, if you're interested. So let's see how this helps us in our finding solutions to linear congruences. So let's return to ax congruent to b mod m. If we have an inverse of a, let's call it c, because we're using b already, then we can use the exact same strategy that we used up here. We can just multiply both sides by the inverse. And what we get is cax on this side, and that's congruent to c times b mod m. But the point is that c times a is congruent to 1. So this is congruent to x. And so this essentially is telling you what is x mod m, and from there you can easily see what your solutions are. So let's see an example of this. What do inverses look like? So what is an inverse of 17 mod 22? So I claim that 13 is an inverse, and we can check that just by doing the multiplication. So 13 times 17. I do not know how to do that in my head, but luckily I came prepared and wrote it down. This is 221. And that's actually pretty clear. 220 is definitely a multiple of 22. So this is congruent to 1 mod 22. So that is showing us that 13 and 17 are inverse mod 22 because the product is congruent to 1. So how can we solve something like 17x is congruent to 5 mod 22? Well, we have our inverse, so let's multiply both sides by the inverse. And I'm going to leave it off this side because I know that the product is going to be 1. That's what we just checked up here. So we get x congruent to, what is 5 times 13? Again, it's a good thing I wrote that down. 5 times 13, which is 65. So x is congruent to 65 mod 22. So our solutions are basically x is 65 plus any multiple of 22. So what is this? 65, but you could also have 43 or 21, and you could also go up, etc. And maybe it's worth pointing out again, if we want to think about these things in this sort of specific set that we often think of, which we call Z mod M, Z mod 22, then we will always have a unique solution. If we have a solution, it will be unique mod 22. So in this case, 21 is the unique solution mod 22. So here is how we solve linear congruences.